In this video, we will discuss the solution to problem G Penacony from Codeforces round 962, which was a Div3 round. Instead of just looking at the solution, we will also talk about the process of upsolving and the most effective way to read the editorials of Codeforces problems. Towards the end of this video, we will also look at a 5-step roadmap to use Atcoder Library as a black box, just like STL. This video is divided into 3 sections covering different time complexity, and there is no prerequisite for any of these 3 sections. Let's move on to the problem statement. The problem says that you are given n edges on the circle, and initially all the edges are turned off, that is, all the edges are deleted. You are also given a set of friendship pairs. So for example, 1 and 4 can be a friendship pair, and you need to activate the minimum number of edges such that the friends in a friendship pair are reachable via edges. In a contest setting, the first approach that you might come up with is to, let's consider this friendship pair. Suppose it is between node 2 and node 6. It can either be connected via this shorter arc or it can be connected via this longer arc. There is only 2 possibilities. So you might think that fixing one of these arcs might help you towards some insight that will help you solve the problem. But that is not true. That is actually a dead end. And why is that? Because suppose you fix this shorter arc, then you can compress all of these 3 nodes into a mega node, and you will land onto the same problem but on a smaller space. So you haven't really simplified anything. So we need to come up with some different approach. At this point, I was completely out of ideas. So I decided to look at the editorial for some hints and keywords. Luckily, the first line of the editorial says that try to fix an edge that will be deleted in your optimal answer and then analyze the problem. So let us do that. Suppose the edge between node 2 and node 3 will be deleted in the optimal answer. Then you can notice that there will be exactly one path between any 2 vertices. So you can iterate over all the friendship pairs, and suppose that the friendship pair that we are considering is between node 4 and node 1. For this particular pair, you can iterate over the unique path between them and activate all the edges that you encounter in between them. If you do this for all the edges considered as the choice for deletion, you would have solved the problem in O of n into m into n. So this n is for the choice of the deleted edge. This is for iterating over the friendship pairs, and this n comes from the fact that to traverse the path between any 2 vertices, you might have to end up traveling the entire circle. You can keep a boolean array indicating whether an edge has been activated or not. So you see that this was such a simple but such a powerful observation that it led us to the correct solution in a minute. Although the time complexity is not optimal, but we at least have one working solution, and then we can try to optimize the time complexity. In fact, I would argue that given the problem statement and also given this particular hint, the difficulty of the problem reduces from 2400 to just 2000. So how do you improve your analytical skills so that you can also come up with such observation? And the answer to that is to upsolve more problems and read the editorials for those problems. When people ask you to practice problems and read editorials, they don't necessarily mean that you need to learn new algorithms and data structures from these editorials. No, that should not be a priority. Instead, your goal should be to learn about new ideas and techniques. You should focus on mimicking the editorialist, like what are the observations that they come up with. For example, if you are new to competitive programming, when you read an editorial, you come across an observation that you might think is so out of the blue that you could have never come up with it during the contest. So, how did the editorialist even come up with that observation? And the reason is practice and experience. In fact, in retrospect, you can even argue that this observation was also very intuitive to experienced players. And why is that? Because you might have solved problems where instead of finding the number of elements in a good set, you compute the number of elements in a bad set instead. So if this problem was asking you to activate some edges, the complement of the problem is to delete some edges. So why did you not think of the bad sets instead? So one can argue that this is intuitive, but this is intuitive only for those people who have solved a lot of problems on similar theme. And you can also do the same by upsolving old problems, reading the editorials, and focusing on the ideas behind the problem, not just on the algorithms and the standard data structures. Once you fix the choice of the deleted edge, for each friendship pair, you are iterating through all the edges in the unique path between them, and you are activating all of these edges. But notice that the path between two vertices is either a subarray or it is a combination of a suffix and a prefix. And when will this combination occur? It will occur once you cross over from the nth element to the first element. Therefore, you are looking for a data structure that can efficiently set multiple elements in a range or in a subarray to 1. But sadly for us, such a data structure does not exist. So we need to get a bit more creative. Instead of setting the entire subarray as 1, let us increment all the array values or the subarray values by 1. If you do that, you can see that you can still recover the answer. That is, after you have iterated through all the friendship pairs, you can go through each edge and check its value. If its value is strictly greater than 0, then it means that this edge has been activated at least one time. Therefore, it needs to be in the answer. So you can still recover your answer if you do range increments instead of range set. But now that you have transformed the problem, do you know of a data structure that can efficiently support incrementing all the elements in a range by 1? Yes, that data structure is the difference array. Because if you are incrementing all the elements in a range by the same amount, the difference between them doesn't change except for at most 2 elements. So you can maintain a difference array so that you would not need to traverse this entire circle every time you encounter a friendship pair. And in this manner, you can solve the problem in O of n into m. So this n is for fixing the choice of the deleted edge. This m is for iterating through the friendship pair. And for each pair, you are just querying the difference array, which is O of 1. So we have solved the problem in O of n into m by getting a bit more creative by incrementing a range instead of setting it to 1. By the way, the answer to this question is yes, there does exist a data structure that can set all the elements in a range to 1 if you are talking about a binary array. But I'll let you answer that question in the comment section below. To improve the time complexity even further, notice that for each choice of the deleted edge, it is not feasible to iterate over all the friendship pairs because that will introduce a product of m in the time complexity. Therefore, it is clear that we need to reuse some of the information from the previous choice of the deleted edge, just like we do in dynamic programming problems. So now, suppose that in the previous iteration, we deleted this edge, and in the current iteration, we are planning to delete this edge. Let us see what friendship pairs will be impacted. Obviously, the only pairs that would be impacted are the ones that were planning to use this edge but could not because it was not available, or the ones that were using this edge but they will now be impacted because this edge is now gone. What is common between all of these? The common link between all of them is that all of these pairs will necessarily contain node 2 as their endpoint. Therefore, it is clear that we only need to analyze the pairs where one endpoint is node 2. Now suppose that the other endpoint is node 5. In the previous iteration, when this edge was not there, they were connected like so. But now that this edge is gone, the path will have to cross over from the nth vertex, come to the first vertex, and then arrive over here. So we can subtract 1 from this subarray 2 to 5, and then we can add 1 to this suffix and 1 to this prefix. Let's consider another example. Suppose one endpoint is node 1 and one endpoint is node 2. When this edge was missing, it had to take a longer route. So it had to cross over from the nth vertex and then come to this node 2. But now that this edge is back, it will simply take the shorter route and it will not cross over anymore. Therefore, it is clear that if a path crossed over from the nth vertex previously, it will not cross over anymore, and vice versa. Therefore, we can say that for every path where one of the endpoint is 2, their orientation is flipped, and that is why we can accordingly subtract the contribution from the previous orientation and add the contribution to the new orientation. And if we do this for each of these shifts, you can notice that all the shifts are performed in O of 1 and there are n shifts, so the overall time complexity is O of n plus m. Why is it n plus m? Because in each iteration you are only iterating through the adjacency list of a certain element, and if you do that for all the n nodes, it is equal to the summation of degree, which is of the order of m. So this solves the problem in almost O of n plus m. But there is one subtle bug that we have introduced while we were optimizing for the friendship pairs. And that bug is that when you were deleting this edge in the previous iteration, after you were done with all the friendship pairs, you did convert your difference array to a prefix sum arrays so that you can iterate through all the edges and figure out which one have value strictly greater than 0. And the catch with difference array is that you can only do the point queries after all the range updates. But now you see that you need to do range updates, point query, range updates, point queries, and so on. So that is why your difference array technique will not work anymore. So in the remaining section of the video, we will talk about a new data structure that can support this operation of incrementing certain things in a range and then finding out the number of non-zero elements in a range, so that we do not have to perform O of n operations in each iteration of the loop. And another thing that you can notice that is that even though the difference array works in O of 1, in this approach, after you are done with all the friendship pair, you did convert your difference array to the prefix sum array. So while doing that, you already added an n factor to the time complexity, which is something that we do not want. But as far as the logic of the problem goes, we are done. Like, we are just looking for a data structure that can support these operations efficiently. But other than that, we have solved the original problem. To figure out this data structure, we need to get creative. Remember that the editorial used a trick of computing the bad sets instead of the good sets. So why can't we do the same thing here? We know that possibly no such data structure exists that can find the number of non-zero elements in a range. So why don't we try to look for data structure that can add a delta to a subarray and then query the number of zeros in a range? Because we can still recover the answer from this. The answer would be n minus number of zeros, because the number of zeros would indicate the edges that have not been activated at least once. But sadly for us, even this data structure does not exist. So we need to get a bit more creative. So one observation you can notice is that the array that you have, that will only contain non-negative integers. Why? Because it contains the number of times an edge has been activated, which can either be 0 or more than 0. So can we say that instead of querying the number of zeros, we are querying for the frequency of the minimum element, because we already know that the minimum element will be 0. So we are querying for the frequency of the minimum element. And now we are talking in the realm of actual data structure, because all the theory that you might have read on the internet, they mostly talk about increments and minimum. And this is what we want. That is, we want a data structure that can add some delta to a subarray or to a suffix and a prefix, and it should be able to query the minimum element of the entire array, and we already know the answer that it is going to be 0, but it should also tell us the frequency of the minimum element, and it should do that in O of log n. So if such data structure exists, our task would be done. So this problem is fairly trivial if you know segment tree even as a black box. And in fact, this problem has appeared in a recent Atcoder contest, Atcoder beginner contest, in problem called second largest. I will link this problem in the YouTube comments. You can attempt that problem first so that you gain some more experience with using normal segment tree as a black box from Atcoder. So after seeing this, I immediately know that it is fairly easy to answer this query with segment tree. It was also fairly easy to answer this query with segment tree, but it was not possible to answer the combination of both these queries with normal segment trees. So there does exist a data structure that can answer a combination of both of these, and that data structure is called lazy segment tree. But before you close this video thinking that lazy segment tree is way above your skill level and you should not learn about it immediately, let me reassure you by saying that this is also my first problem on lazy segment tree. And in fact, you do not need to know all the internal details of lazy segment tree to use it. In this video, I will show you how to use it as a black box. But before you do that, make sure that you also attempt this problem so that you get hands-on experience with normal segment tree. And the reason why I am encouraging you to use Atcoder's lazy segment tree library, even though it is an advanced data structure, is because you must have already been using sets in STL. But do you know how sets are implemented behind the scenes? It is actually implemented as red black trees. So do you know all the internal details of red black trees? Possibly not, right? But you still use sets. So what is the difference between sets and lazy segment tree as a black box? There is no difference as such. So you should learn how to use this as a black box. So in the remaining section of the video, I will share a roadmap with you using which you can write your own template for using the lazy segment tree from the Atcoder library. But notice that to arrive at this simplification, we needed to get creative with the query that we wanted. That is, if you just wanted the number of positive elements, you had nowhere, right? Like that led to nowhere. That was a dead end. So we converted it to the complement set. So we wanted to query the number of zeros. But we know that this was not something that is available on the internet. But then we noticed a clever observation that 0 is equal to the minimum element, so we are querying for the frequency of the minimum element, and that is why we arrived over here. So I would like to share a similar problem that I encountered on Codeforces a couple of months back, where this creativity was involved, and let me know how you would solve this problem in the comment section in YouTube. So the problem is that you are given an array and you are given multiple queries. In each query you need to answer yes or no depending upon whether all the elements in a range are equal or not. And there can be two versions. First of all, assume that the array elements do not change, then there is a very simple solution for this. And then secondly, assume that the array elements can change. So how do you efficiently answer this query? Let me know your approach in the comments. There are 5 steps to solve a problem using lazy segment tree from Atcoder Library. First of all, you need to write a wrapper with whatever features that you need from the lazy segment tree. In this problem, we are looking for a data structure that can add a delta to a range. So we will write a brute force implementation. That is, we will iterate through all the elements in the range and add the delta. And the second feature that we need is computing the frequency of the minimum element. So we iterate through the range, figure out the minimum element, and then we figure out the frequency. This is to ensure that there is no other bug in your code apart from it being slow. Because once you add lazy segment tree, it becomes very difficult for you to debug any issues with the lazy segment tree, because that is a black box. So in order to add that black box, first of all you need to make sure that the rest of your code is correct. Then we need to solve the problem. To do that, you can assume that in the 0th iteration we will delete the edge between node n and node 1. So in this manner there can be no crossovers. So that is why the path between any two nodes is equal to the subarray between them. So we add a 1 to each element of that subarray, and we also maintain a map corresponding to whether a crossover has happened for any pair of friends or not. And by crossover I mean whether we jumped from the nth vertex to the first vertex. Then we will repeatedly keep on deleting the next choice of the edge, and we already discussed that only the pairs that would be affected will be the ones where one endpoint is equal to x. And for that, all the nodes that will be affected, we figure out whether there was a crossover in the previous iteration or not. So if there was no crossover, we will simply remove the contribution of that subarray and then add a crossover by incrementing the suffix and the prefix. But if there was a crossover, we need to remove the contribution from the suffix and prefix and then increment the subarray. And then we already know that for all the pairs for which this is an endpoint, the crossovers would flip. And at the end, once we have done all of these, we can query our data structure that we just created to figure out the frequency of the minimum element. So using this simple code, you can see that we have solved the problem, and the only suboptimal part or the only slow part is querying these functions that has complexity O of n. So in the remaining section of this video, we will see how to optimize this using the Atcoder's segment tree. Then we need to handle the query part of the segment tree, and after that we will handle the update part of the segment tree. To handle the query part, think about what you need as an output from the segment tree. You need the value of the minimum element as well as its frequency. So therefore, let us maintain a data structure that will store the value of the minimum element here and the value of the frequency here. Then you need to add two functions. The first function is called op. This function will have two parameters A and B, and let me tell you what these two parameters represent. Suppose that you want the minimum element and its frequency of this entire array. Let's partition this array into two parts, the first part and the second part. If someone tells you the minimum element and its frequency of the first part, and also tells you the minimum element and its frequency of the second part, can you tell me the minimum element of the entire array as well as its frequency? So that is what this A and B represents. So this A and B represents the answer for this left segment and the answer for this right segment. And the return value of this function is equal to this answer for the entire segment. So you can see that it is very easy to combine the answers. That is, if the minimum element of both the segment is equal, you know that that will be the minimum element of the entire segment as well, and its frequency will be added. So that is why if the minimum element is equal, the minimum element of the entire segment is also the same and the frequency gets added. But if the minimum element of this is smaller, then we don't care about the frequency of the bigger element here, right? So the smaller element in the entire array will be whatever is smaller in between them. So that is why we return the smaller element. This is the first function. So if in future you are using this op function, just remember this interpretation. That is, A represents the answer of the left segment, B represents the answer of the right segment, and Atcoder is asking you the answer for the combined segment. Then you need to add an identity element which should be equal to the answer that you want when the array is empty. So if the array is empty and you are querying for the minimum element, let's just return infinity with frequency 0. In the previous slide, the data structure that we created called S was the return value of the queries that you wanted. In this slide, the data structure that we will create will handle the range updates to the elements of the subarray. So you know that you will be adding some elements to the subarrays. So that is why I will use f as integers, because we are adding some delta to a subarray. Then we need to create a function called composition. And let me give you the interpretation of this function, what it gives you as argument and what it expects. So it is basically saying you that if you want to add a delta called L in your subarray, and you also want to add a delta called R in your subarray, can you tell me just one single delta that I need to add so that I don't need to maintain both of these values? So in that case, you can see that if you want to add 2 to all the elements of the subarray and you also want to add 5 to all the elements of the subarray, in short, you can say that you want to add 2 plus 3 is equals to 5 to all the subarrays. So the return value should be equal to the combination of these f values, so that you don't have to track multiple values anymore. And you also need to create another value called id. You also need to create another function called id, and this represents that if I add this identity element to the subarray, nothing should change. And this is obvious that if you add 0 to a subarray, nothing will change. So this is why we have added 0 as the identity element. So this is also clear, just like S. The last thing that is remaining is a function called mapping, and this is a bit tricky. So for this function, the arguments is f and x, and you need to figure out f of x. So if I were to give you the watered down version, I would say that consider an element x and remember that s is the data type of the return query. So this function tells you that if you just have one single element x and you apply this delta to that element, what is the answer that you want me to return? So you can see that if you already have the minimum element and its frequency and you apply a delta of f to that single element, what is the answer that you would expect? You would expect that the value of the minimum element increases by the delta, but its frequency does not change. So that is what this function wants from you. It basically tells you that if you have the answer from the previous query and if you were to apply this delta, what is the answer that you want me to give you back. So this is the mapping function. So we have seen that we have first defined a data type called S, we have defined a data type called F, and we have defined a function called mapping, and I have given you the interpretation of all of these functions. Now keep in mind that all of these interpretation are highly specific to the problem we discussed, but that is alright, because most of the problems that you use lazy segment tree in will mostly concern minimum, maximum, and some delta, right? So all of this logic should still work. But if you want a theoretical definition of what exactly composition is, what mapping is, etc., you can take a look at the official documentation of Atcoder library. Finally, the last step is to add the constructor to create the lazy segment tree and then replace the wrapper function that you had created. Now, to create the constructor for the lazy segment tree, first of all you need to create an array, and the data type of that array should be the return type of the query. And remember that the return type of the query had data type as S, because the data type called F was just for adding the delta. The only thing that would be returned is the answer of the query, and the data type for that is S. So you create an empty array with the return type of the query, and you set that you initialize it with 0, because every element has a value 0 with frequency 1. So you initialize it like so. Once you have created this vector of S, you can use this line called new lazy segment tree, and you can pass this same vector over here to create the segment tree. So now your lazy segment tree has been created. Then you can use this same function signature and replace the implementation. So if you want to add something in the range L to R, you can use a function called apply that applies this delta from L to R. However, I am adding a +1 over here, because be careful, the Atcoder library has close open range. That is, just like STL has dot begin dot end, and dot end should not be accessed, therefore it has L and R+1, where R+1 should not be accessed, that means R should be accessed, which is what we want. And if you want to query the frequency of the minimum element, you just use a function called prod with the same logic as before, the close open range, and then this will give you the frequency of the minimum element as well as the minimum element. So you extract the frequency and send it. So now you can see that using these 5 steps, you can utilize Atcoder's lazy segment tree to solve this problem in n log n. Why? Because this query works in log n and this query also works in log n. Now I hope you realize the power of Atcoder's library, because in the initial days of competitive programmings, whenever you had to learn segment tree or whenever you had to learn lazy segment tree, you would not be able to use it as a black box, because every time there was any little modification, you had to think about a lot of things. So first of all, you had to think about how the queries can be combined, and then you had to think about range updates separately. But with Atcoder, you don't even need to think about how the point updates or range updates will happen, because it only asks you how do you want to combine the queries, and it says that, hey, let me handle the updates, you just tell me how to combine the queries. So that is why you only see a single function called op in a normal segment tree. But if you were to write your own normal segment tree, and if you read blogs online, it will ask you to think about 2 things. One is how to combine the queries, and the second is how to do the point updates. But Atcoder eases the task for you and asks you only how to combine these results, right? It says that it will handle all the point updates behind the scene, so you don't need to worry about that. So this is how you can use lazy segment tree. And like I told you before, that this is also my first time using lazy segment tree. But it's not that you need to be afraid of it or anything, okay, because even if you do not use lazy segment tree in future, you just need to remember that there is a data structure that supports these operations, and if and when the time comes, you will be able to reference the documentation and use that data structure. So yeah, credits to Aryan. After looking at his code only, I figured out that this vector was needed to write the constructor for this. But the bottom line is this: if you think that the lazy segment tree that we discussed in this video is too intimidating for you, you can completely skip the Atcoder library part from this video. That is completely fine. But make sure that whatever wrapper that you are writing, that should have the same signature that the lazy segment tree will have. And as long as you do that, it is not compulsory for you at all to get an AC using lazy segment tree. As long as your wrapper is something that can be replaced blindly with a template from the Atcoder library, you should be okay. And in fact, I have added the easy version of this problem in the Codeforces group, so you can submit your solution over there. And as long as you can convince yourself that the remaining stuff is just replacing this black box with segment tree, then you are done. But that should only be done once you are sure that the replacement exists, because if you are writing something like replace all these values by all these values to 1, so you cannot assume that a replacement for this exists, right? So you need to write your wrapper in that manner. Now, if you are confused about how to use the Atcoder library to submit on Codeforces, for that, Aryan already has a video on his YouTube channel, and you can take a look at that video. I link it in the comment sections below. And if you have any more queries, you can ask on his Discord server if you are facing any configuration issues in setting up the Atcoder library on your system. The code, practice problems, etc. and the slides for this video will be available on cfstep.com.